Most of the time, as we have discussed, for an existing concrete beam or slab with excessive deflection, simple external bonded system with FRP or steel jacketing will not work. Typically, we go for hybrid post-tensioning plus other systems. What are the other systems? It could be post-tensioning system on the beam, and then you have a concrete overlay at the top surface of the slab, and then PT plus shear collar if you have a flat plate system, or a PT plus drop panel, or a PT plus concrete enlargement. So, different combinations can be chosen to improve the performance of a PT slab. And this is the way that typically we do. So, you design an anchor plate and you drill a hole through the column. Of course, when you drill a hole through the column, we have to choose locations in such a way that through holes when you put it, of course, it should not cut the column reinforcement. So, we have to do some NDT measurement to find out the locations where the steel is not there, then we cut through it to put the through bolt so that this bearing plate can be anchored. So, now you can see that we create a cable like this and then we put a saddle or a deviator and then we create a slope change. Now, you can see here this is your slope change, we see it is going to be 2p sin theta is a force that I am going to put. And you find that by adjusting the height of this saddle or deviator, now I can create higher sin theta. Higher the theta, higher will be your vertical push. So, I can adjust depending upon your site considerations, the height of the saddle and also the number of cables that is required to create an uplift force, how much is required. And now, this is again another example where you can see for a slab system which is strengthened using external PT cable by providing this kind of a saddle or a deviator. So, this is nothing but a saddle or a deviator, and you can see that it is done in the both the directions, right. So, two-way slabs need strengthening in both the directions. So, we need to do the same for alleviating the deflection issues in both the directions. Okay, now, what are the details of the anchoring system? So, as you can see here, PT system is designed using a fixed anchorage system located towards each end of the beam or slab. So, you can see this kind of anchor systems that is designed, right, and then you also have a post tensioning cable depending upon the amount of cable that is force that is required. So, you can see now in this case you have 3 plus 3 total 6 cables are there, 6 individual half-inch strand cables have been put, and now when I calculate the overall CG of this all this strand, I have to take the CG of the group of these cables and then do the calculations, right. So, now in this case you can see here you have number of cables that are running both in the longitudinal direction as well as in the transverse direction, and you have to generate that reaction. So, when you do the generation of a reaction, so you can see that always you have this is your CG of the concrete and this is your CG of the table. So, you get this eccentricity. So, P into E is your eccentricity moment, that pre-stressing moment that you create along the length of the beam, right. Now, the post tensioning cable can be bonded or unbonded along its entire length, right. So, the end anchorage system can be made either in concrete, that is doubled into the existing concrete, or they could be manufactured of a structural steel and bolted. For example, this is structural steel that is bolted to the parent concrete beam. Similarly, you see here this is your anchorage system which is bolted to an existing concrete beam, right. So, now in this case this is external, but here these external cables are also now you will be adding additional layer of concrete. So, that absolutely there is no problem, corrosion is not an issue, and then maybe the strengthening increase requirement is very high. So, that is the reason this combination of your external PT and concrete enlargement is chosen for the system. This is your slab strengthening, and you can see here fire resistance, because these external PTs are outside the structural element, they are not within the concrete. So, sometimes during a fire rating you will have issues. So, fire resistance or protection is always an issue, and typically just like for FRP system or your steel, fire protection is done through some fire insulation. Either you can have the self-furring metal lath, where within that you can put a cable, or you can have this vermiculite plaster, which is very commonly used. So, you put this vermiculite material and create the fireproofing. Of course, the thickness of the vermiculite plaster will actually determine the fire resistance of the post-tension cable. Sometimes the anchoring may not be possible from the ends. So, what you do is, if you do not have any exterior access to create that anchoring zones, then what we can do is we can also use this self-equilibrating center anchor. So, you basically self-equilibrating, so one reaction will try to balance each other. So, when I pull on this side, I can react against this particular element, and that itself will act as a self-equilibrating center anchor. So, this is also very commonly used when you do not have any exterior access to drill a hole and put the anchor. And as you can see, it can be used for both one-way slab and slab girder system. So, for one-way slab it is pretty easy. So, you can see that you drill a hole and then design your thickness of your deviator in such a way to determine how much is this upward force, right. And when you do that, of course, there is some downward load also created, but the download goes to the column, which can be easily taken care. But if you see, we are interested in how much upward force that we are creating on the slab element. Now, this is for a slab beam element. Again, we can see this, you can create a deviator block and apply the same concept. Now, the anchorages can be done on the column in the transverse direction as well. Now, this could be for a continuous system as well. That is what we see here, that the cable actually goes continuous and it is going to follow the bending moment profile. So, the principles of a cable remain the same, whether it is going to be within the concrete or an external system. You should actually follow the bending moment that you are going to get from an externally applied load. Okay, this is another classical example of a double T girder. When you have a long span, typically in a precast system, people use double T girders as well. In parking garages, these double T girders are very, very common, and over a period of time, maybe due to increased live loads or maybe because of the deterioration, sometimes we have to go for strengthening, and that also, if you look at it overall in the longitudinal direction, I can design a cable system like this, right, and that is going to create an upward force like this, and it is going to create an upward deflection because of this. That is going to nullify this is your upward deflection. That is going to actually create a camber, and the external load will actually try to balance, right. So, the external PT can be used for creating uplift to address the deflection issues in a double T girder. And again, these are added as an external element to an existing element, right. Now, if I am not doing concrete enlargement, they are always visible, and fireproofing can be an issue. So, that has to be thought through carefully, right. Now, two-way slabs, I mean the concept is the same, and as we have seen in PT flat slabs, we are actually converting the two-way slabs into frame into orthogonal direction, and we are designing it as an one-way system only, right. The same way, two-way slabs, you will have two-way bending. So, ideally what we can do is, you will have, if you are running a cable like this from column to column in a diagonal direction, and you take the anchorages from the column, then it will create an upward load in this direction. But what will happen is, this diagonal PT is very difficult to implement it in the slab, particularly when you have a square or a rectangular column, because it is very difficult to install the anchorages in the corner regions. So, it is very difficult to implement it, though it is, we know that intuitively this way in two orthogonal to cross directions, if you put an external PT cable, it is going to help in relieving that deflection of a two-way slab. And we have studied that two-way slab, typically strength is not an issue, it is a deflection that will control the design. So, PT can be easily designed to address the deflection related issues in a two-way slab. So, practically what people do is they run two truss systems, right, in the orthogonal direction. So, basically what we do is we again create two saddles in such a way that majority of the upward load is created in the middle, that is going to create an upward camber. At the same time, to create that, some level of downward reaction like this will come. Now, but then again I can design the orthogonal direction in such a way that this upward force is going to balance this green color downward force. So, the net effect is still going to be upward. So, I can play with the deviator or saddle dimension and the amount of pre-stressing cable to create always a higher uplift than the downward reaction that I am actually creating here. Right. So, that is also possible. So, people have implemented such systems for a two-way system. So, this is one example. You can see here that you have actually created a truss system with a PT cable, and this is your, you can see also that vermiculite plastering is done for fireproofing. Right. So, this is A saddle and B saddle, and I designed the cable in such a way that the downward force what I am creating in this B saddle is going to be lesser than the upward force that I am creating, right. So, that is what it is, So, the net effect is always you are creating an uplift force, so that it is going to help in relieving the effect of your external loads under service conditions. Okay. Now, for bridge strengthening, again external PT is quite commonly used, and you can see that post tensioning in hammerhead piers, which is a very common type of pier heads, which will be subjected to significant bending and shear. So, I can run an external cable like this, and then I can do the PT cabling, right. And then for a post tensioning in the top slab of a box girder, I can again create and install this PT cable like this. Then I can, for a box girder, I can also do the transverse post tensioning like this, and then I can also create a vertical post tensioning to create or improve the shear performance, right. All these things are possible, and PT in that way is a very elegant method to improve both the shear capacity, flexural capacity, and also to reduce the effect of your deflection. Okay. So, whenever we do the strengthening, obviously for an externally reinforcing systems which are susceptible to damage, then I always have some strengthening limits. So, what are the strengthening limits? So, ACI 562, it gives you some strengthening limits, right. So, 561. So, you see here, for the increased loads, I have to satisfy that revised strength nominal capacities should be at least greater than 1.1 times dead load, 0.5 times live load plus 0.2 times your snow load, or it should be greater than 1.1 times D plus 0.75 times your live load. So, in a way what we are saying that is, even without this external reinforcement, the structure should be able to satisfy the service loads. So, that is the whole point. Even due to some reasons, if your external system is getting lost, still the structure should be able to sustain its live loads, so that it gives time for the people to evacuate before you take up any structural remediation efforts. So, we have to satisfy both the limits. So, indirectly what it is saying is, you can only increase so much the strength, right. So, that is what the code is saying. But if lot of fireproofing is done, then we can, you have to take a call, engineering judgment, how much leverage that you can give for increasing the strengthening limit. And typically fireproofing is recommended to protect the external reinforcement for minimum hours of fire rating, right. So, then we have to, for a critical structure, obviously we need to go for a fireproofing, so that for minimum periods of life, so the fire rating, the structural intervention that what you have done, it should not be damaged. And this is what we talked about. The fireproofing is typically done using the vermiculite plaster or providing some kind of another insulation in the form of an intumescent paint coat, or the NPTEL cable can be put in a duct and then they can be grouted as well. So that under the action of fire, again they don't heat it up and then they lose this capacity quickly. And again, external PT is very quite commonly used for strengthening the pipes. You can see that we all know that for a pipe which is transporting any form of a liquid, then it is going to be subjected to heavy internal pressure. The internal pressure is going to create a hoop tension. Now, because of the hoop tension, you are going to create a lot of cracks, and to arrest this, what we do is by this external PT, I can create a compression that can offset the hoop tension that it is developed. In that way, the pipes will not be cracked and you can easily implement it in the field as well. Of course, a lot of effort is required, but it's much more elegant way of actually tackling the tension that is coming from your heavy internal pressure of the fluid that is transported across this pipe. Now, how these cables are joined? These cables are joined using this two-way stressing anchors. So, you can see one end of the cable goes like this, another end goes like this. So, in that way you can loop the PT cable in the circular direction. And this is again for silo strengthening, same. So, there is a vertical element and you can closely look at it. One cable goes like this, another cable comes on like this. So, you can run multiple cables to create that compression stress, so that under hoop tension it is not going to lead to crack and other serviceability issues related to this storing of the material in the silos. So, again another example where this external PT is used, for example, due to some reasons, change in the purpose of the building. Let us say if you want to remove this column, and if you remove the column, obviously the span becomes double and your deflection is always 4th to the power. So, deflection is span to the power of 4. So, when you double the span, in fact, you increase the deflections quite dramatically, right. So, to address this, now again I can add an external PT cable, and also that can be designed to create an uplift force, so that the deflection issues are sorted out. In the same time, you can also combine this PT cable along with concrete jacketing. For example, you see here, so the concrete jacketing right in the middle, you have high eccentricity and I can encase it with some additional reinforcement, shear dowel, and this is your new concrete, right. And we can put some holes on the top of the slab, so that the pouring along the length of the beam becomes easy as well. So, this is a section at mid span. Now, at support you can see here the cable profile, it goes to here. So, the eccentricity is E here, and here you can see the eccentricity is E here, right. So, in this way I can create a cable profile in line with the bending moment that what we are going to get from your external loads. Of course, the bonding of the old concrete and new concrete has to be ensured really well. So, you need to put your shear connectors at 300 millimeter on center. So, to make sure that the interface between the new concrete and old concrete is really going to act as a one single unit. And this is again another common applications where instead of PT cables, we can also use Dividag bars. These are very solid bars, thick bars that can be used for pre-stressing reinforced concrete element. We have seen now in number of this extra dose bridges and cable stayed bridges, these kind of anchor bolt systems are very common. This anchor nut actually absorbs the tensioning force from the post-tensioning bar and rests on the anchor plate, which again further transfers the tension force to the concrete. So, this is the system, and all of the components used for Dividag bar synthesis are actually threadable, and you can thread it and to whatever the level that you want, and thus it helps for quick and easy and safe installation. And again, proper grouting is also important in protecting the steel from corrosion, and thus contributes to significantly to the strength of it. So, we need to protect these bars which are externally there. So, or we have to make sure that they are corrosion resistant. Now, for this is for strengthening for a heavy vehicular load, we can combine post tensioning plus some concrete overlay, and you can see that in an existing concrete floor slab, this kind of overlay can be added. Now, when I do this kind of overlay, what I do is I increase the effective depth for the steel in the girder below. So, in that way, I am increasing your flexural strength. Now that the thickness of the slab is increased, the shear capacity is also going to go up, right. But again, the thickness of the overlay add lot of weight to the existing element. So, that also we need to be careful, right. So, in addition to that, I can also use this FRP based laminate strengthening, and these are passive systems, but that helps in addressing the reinforcement requirements on the tension side. In addition to that, I can also put external PT that can help in improving the strength as well as recovering the deflections. Then in top of that, I can also put overlay. Nowadays, this for bridge decks, the ultra high performance concrete overlay are getting very increasingly used because of its versatile nature. It has very high compressive strength, and it is also going to create an impermeable layer on the top surface of the deck slab. So, corrosion issues are sorted out. So, combinations of post tensioning, FRP and concrete overlay is very effective technique for strength enhancement and reducing the deflection. So, these kind of techniques can also be used in combinations, so that they are going to act together to improve the performance of the structural element. Now, this is again another example where how we are using external PT which is encased in concrete. For example, you see this PT cables, high strength PT bars are do. In addition to that, we are also putting some shear dowels and increasing the thickness of this pier cap, so that we can transverse post tensioning is done. In addition to that, this new concrete is going to encase this PT, so that the corrosion issues are also sorted out. Now, these kind of end anchors are also there. So, these are the different types of anchors. This we talked about center stressing anchors, right. This center stressing anchors is quite common, right. And then we have this the middle strength stressing anchors, and then these kind of end anchors are also there, and deviator blocks, different types are being used for creating the cable profile what we want, right. So, the external components whatever that is used in PT. Now, how do we create or embed an anchor block, right. So, we have to now sometimes use this roto hammer to create the holes, and of course, for putting the holes in the concrete element, we have to do some NDT measurement to make sure that we are not cutting through important rebars, and for cutting large holes, these kind of core cutters are used, so that you can put the anchor block inside and then react against it for creating the pre-stressing what we want. And most of the time when we do this concrete enlargement, we try to use the self-consolidating concrete and self-consolidating concrete, so that most of the time we do the overhead applications, and we want this new concrete to penetrate well with the old concrete. And sometimes we also put fiber reinforced concrete to increase the shear strength, right. So, for that again at the material level, lot of trials have to be done, so that the interface bond is ensured and we are able to place the concrete easily without lot of vibration, and it should also bond well with the existing new old concrete, right. Now, we are going to another system which is an external post tensioning system for column strengthening, which is the system that was developed by Professor Murat Sarkioglu, and you can see that this is a very elegant system that is proposed, which is calling it as retro belt system. So, in this retro belt system, what we are doing is we are doing the external PT with the cable, and just like a belt that we are putting to our trousers. So, basically this is the belt system that has been designed for creating this confinement through external PT. Of course, to keep this cable profile, these kind of external elements have to be fabricated nicely, so that you can apply this pre-stressing easily. The whole concept is very simple. We are inducing confinement to the concrete column. We know that whenever concrete is subjected to external confinement, the strength and ductility of the element increases significantly, right. So, that is a concept. So, this is designed to provide lateral confinement, just like we do externally FRP bonded system for improving the confinement. It provides external pressure to the concrete and it is going to improve the strength and ductility, and it is going to help in crack control. It prevents diagonal tension cracks, particularly when the columns are subjected to heavy shear load, and it strengthens the splice regions where you have, let us say, if you do not have adequate lap splice length, then by confinement I can improve the bond and it increase the ductility as we have discussed. So, that is going to help me in improving the flexibility and deformation ability and shear capacity improvement as well. So, because of this external confinement again, and PT also acts as an additional stirrup. So, it is going to enhance the shear resistance to the applied shear forces. And how do we do that? I think this is very easily that you can see here. After the marking, I think you can see that this can be installed just like a belt, and we apply required amount of post tensioning force, and then we anchor them, and you can design the diameter and the force of the cable and also the spacing of this particular PT system in such a way to the improvement in strength and performance what we are actually expecting. So, you could see one of the column that has been done with the external PT. You could see that cables are all spaced nicely uniformly throughout the entire length of the column. Now, if you want more, for example, if the column is having lap splice issues in the bottom, then I will design the more PT cables in the bottom and then I taper it down as we go to the top. So, multiple ways with which we can actually design this particular system. Now, we know that for a square column again confinement is difficult. So, we have to design these systems so that you do not create the stress concentration. So, this kind of an external system has to be created so that you can create that external PT cable at that location to create that clamping force what we want. Particularly this will be quite effective when you have a column which are more rectilinear. That means when your aspect ratio, let us say breadth to depth, or I should say is greater than 2, not the height. So, let us say B by A is greater than 2, when the column becomes more rectangular, then the confinement does not really work that much in increasing the strength, and the area of the cross section where it is going to be confined will be very less compared to the overall area of the cross section area of the column. So, for such kind of system, that is why the externally bonded FRP system, they do not really work well, particularly from strength improvement point of view, though ductility there is some help. For such kind of highly rectilinear columns and for large size columns where FRP confinement will not be very efficient, this kind of system will be quite attractive. So, they have published, they have carried out full scale testing, they also published quite a good experimental papers which are available. So, you can look for more detail. Just to highlight the results, you could see that one of the column that they have tested, this is a circular column, and they have tested and you can see that it was tested as a cantilever column, and this control column which had 12 numbers of 25 mm longitudinal bars, and it had number 10 hoops at 300 millimeter center to center spacing, and when it was subjected to reversed cyclic loads, you could see that it failed roughly at about a drift of about 1.8 or so. So, 1.8%. So, drift. So, the drift of 1.8% at which the column failed, and also you could see that the area within this force displacement curve is very, very small. That means the hysteresis energy dissipation is very, very small, and these are diameters of 600 millimeter, and all the PT cables were stressed to 25% of the yield strength, and they failed at 1.8%. So, this is one. But the same column after retrofitting with this external PT, this is a control column, no retrofit. Right. The same column 600 mm diameter column, now they put this retro build system, and they tested it again under reversed cyclic load testing, and you could see that it exhibited a very nice hysteresis curve, and the area under this curve basically indicates your energy dissipation under a cyclic load. Compared to the control column, you could see that after retrofitting, the same column is able to dissipate a lot of energy, and it was able to sustain almost up to 5% of drift. So, higher the drift at failure, better is the seismic performance, right. So, it has a very good energy dissipation and ductility, and the retrofitted column failed at about 5% compared to 1.8% that we had it in control column. So, the next one is the non-circular column. So, circular column, we know that it can be confined quite well, but is this retrobuilt system, is it really going to work well for the non-circular or a square column? This is a square column. Again, we can see that same amount of reinforcement and equivalent systems. So, you could see that again this column again failed at about 1.8%, similar to that of circular column, and the same column again square column, after retrofitting it with cables, retrobit externally PT cables, and they were stressed to 25% of their ultimate strength with a spacing of 150 millimeter, you could see that the energy dissipation improved significantly, and again the retrofitted column failed at about 5%, you could see. And so, for both circular columns and square columns of really good size 600 millimeter, you could see that retrobuilt system, external PT system, is really able to improve the performance quite significantly. So, that way external PT can be also used for improving the seismic performance if it is designed properly, and they have been tested also for a near full scale columns, and the performance is quite evident from the improvement in energy dissipation and ductility. And this is again a column with a lot of lap splice. You know, this is a big problem in the old bridge columns that were constructed in the early 60s and 70s, and you could see that the column failed under cyclic load at a much lower drift, roughly at about 1% or so, 1% drift, and again the energy dissipation was very less. The same column with the same lap splice, now after retrofitted with the retrobuilt system with using external PT system, you could see that the energy dissipation improved significantly. Now again the drift, even if you consider 80% drop or 20% drop was their ultimate, it was able to go as high as 5%. So, you could see that retrobuilt system is using external PT, we can increase the performance of old columns which has lap splice issues as well. So, this is one of the column which failed in lap splice due to inadequate lap length, and also you could see the spacing of the rebar, they are quite wide. So, they are not at all good from a seismic point of view. Such kind of columns you cannot demolish it, but it can be retrofitted easily using external PT system, particularly with the retrobuilt system. Okay, now we have to also create this clamping devices so that the cable can stay in its place and create the compression. So, these kind of layout can be created for shear resistance. For confinement, we need to have more such systems. So, either this could be made with steel or they can be precast as well. So, such kind of elements can be precast, and then that can help to hold the cable profile at this particular location, right. So, this is for both, if you want both shear and confinement, you need to have additional such I should say the devices, holding devices, so that the cable can stay as it is and it can create a more uniform lateral compression. Now, most of the time what we do is, in case of an external PT, we try to use this unbonded PT cable, so that from maintenance point of view, tomorrow if you want to put additional cable or change the cable, it is quite easy. And as we have seen in the previous lectures, the tendon is actually prevented from bonding to the concrete and it is free to move relative to the concrete, and the tendon force is transferred to the concrete only by the end anchorages. So, in unbonded system, typically you will have a plastic sheathing, and usually within the sheathing and the strand, you try to put grease for as a corrosive inhibitive coating.